Okay, everyone, good afternoon. Hopefully you all remember to take the quiz by last night. And we have lab 1 is due today by midnight. If you have any questions, let us know. I haven't gotten too many questions. I get the impression it went pretty well. That lab was pretty proud of that lab. Charles developed that last year, and I thought it was pretty slick. The rest of the labs are going to be more hands-on, though, so we're going to start getting into hardware stuff today. So I'm going to quickly go over quiz 2, and then I'm going to do a little tutorial on how to set up the FPGA boards that we're using in the class. Some of you might already know how to do that if you've taken, or if you're taking 313 or 611. We're now using these same boards in 3 classes, but I'm going to go through a quick tutorial on how to set them up and how to get them running, because from this point on we're going to be, as I mentioned, doing more hardware and hands-on related type labs. Okay, so the first question on the quiz was what percentage of an SPI channel's master to slave bandwidth can be utilized when performing a series of signal write transactions, and it's master to slave bandwidth, so it's bidirectional. But this question is asking how much of the bandwidth in one direction can be used. You can, in theory, achieve 100%, because there's no, unlike UART, there's no control bits that have to be transacted. In a daisy chain SPI connection between a master and n slaves, how many clock cycles are required to complete a full exchange? Full exchange meaning that all of the peers on the channel receive data from all the other peers, and in this case it would be, with one slave it would be 8 cycles, with 2 slaves it would be 16 cycles, because remember SPI is like a giant shift register. You have to shift all the bits through, and it operates in units of 8 bits. And with n slaves it would just be 8 times n. What is C-pull and CFA for the exchange below? C-pull is the easy one. It's going to be 1 because the clock is high initially. And CFA is a little bit harder to figure out, but the idea is that if the MOSI and MISO change on the first edge of the clock, then obviously they're meant to be read on the second edge of the clock, so CFA must be 1. If CFA were 0, we'd be reading on the first edge of the clock, and so those 2 signals would have had to have been stabilized earlier than the first edge. Everyone see that? Okay. Okay, what data is written in the transaction below? For this you have to count. It's a transaction. There's at least 2 exchanges, at least 16 clock cycles there. It's hard to actually tell just from looking. You can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16. Yeah. So 2 exchanges, 1 transaction. So the first 8 cycles are the header. That's where you send the address. Master sends the address and what type of operation you're doing. And then the next 8 cycles are the data. In this case, it's a write, so it's the data being written is on MOSI, and we just need to basically count off each bit there in MOSI. Now the tricky part here is when do you actually read the bits. I think everyone has their own way of doing this, but clearly you can see that the data is changing on the falling edge of the clock, so you want to read it on the rising edge, right? So if you look at the rising, you look at the corresponding signal. So it's 11100101, and then its most significant bit first, so you just read it from left to right, right? So if you convert it to hex, this would be E5 in hex. I get that right? I guess I did. The bus protocol, a bus protocol requires 3 wires named DIN, DOUT, and clock. This is just a made-up protocol, by the way. Is it synchronous or asynchronous? Probably synchronous because there's a clock. What bit is missing in the timing diagram below? This is UART. And so we have odd parity. There should be an odd number of 1 bits. So the missing bit is on the transmit side. So we don't include the first bit or the last bit because those are start and stop. So if we count, there's just 1 bit right? And if it's odd parity, that means then that must be a 0, because there should be an odd number of 1 bits in total, except for the start and stop bit. Yeah. 0, right? And then that's what I said, right? Yeah, 0. Yeah, there should be a 0 there because there's a 1 bit. If that missing bit were a 1, then there'd be an even number, and so that wouldn't work because there's odd parity. For an SPI channel with C pole equals 1 and C phi equals 0, when does the data signal change? Oh, sorry. So C pole is 1, which means the clock starts out high, first edge is falling, and so if C phi is 0, we're reading on the first edge, and the first edge is falling edge, so falling, right? Yeah. Okay, any questions? Okay, good. Okay, so now let's talk a little bit about FPGAs. So I have these lecture slides. These lecture slides can serve as kind of a reference when you're getting things set up. Unfortunately, there's a lot of steps here, so it may seem a little gratuitous. Obviously, you get used to it the more you do it, but it gets a little complicated, so bear with me. So first of all, in case you're not in 313 and you haven't taken 611, an FPGA is a field programmable gate array. It's a chip that's basically a blank slate. It's useless when you power it on. It does nothing. It's basically a paperweight until you configure it. So you electronically configure it to act as a arbitrary digital logic circuit, right? So you do a hardware design, and then you put it on the FPGA, and the FPGA takes on the behavior of that logic circuit. FPGAs store that information in a volatile way, though, so if you power off the FPGA, the configuration is lost. If you look inside your car, for instance, it probably has 40-some FPGAs in it. Obviously, you power your car off, so how does that work? Well, each FPGA, generally, when they're deployed in a system, they have a non-volatile RAM that's used to configure them when you power them up. And in fact, these boards that we're using in class do exactly that, because when you first power it up, it configures the FPGA from a configuration stored in SRAM, and that's why it's blinking like this. All of this behavior going on right now is actually being driven by the FPGA, and it was configured from a non-volatile RAM that's not on the chip, it's on the board, but it still configures the FPGA. Now you can change that, by the way. You can reprogram that chip on here if you want this thing to do something else when you power it on. Does that make sense? Okay, so basically FPGAs allow you to do hardware design without having to fabricate a chip, which takes a long time and is very expensive, as you might imagine. The downside is that you get 10 times less transistors or 10 times less gates than you would if you fabbed a chip, and the clock runs 10 times slower. That's the disadvantage. But if you fab a chip, it costs millions of dollars and takes a long time to get it back, and it's very hard to test, and then generally speaking, the first version of it will never work. I've designed, I don't know, 7 or 8 chips in my life, and none of them worked. We taped them out, they came back, none of them worked. Yes?
So when you're talking about fabricating a chip, you mean as opposed to digitally configuring this, you could just have it constructed with that logic circuit built in?
Yeah, so the difference is between, the distinction I'm making is between an FPGA and a ASIC, which is an application-specific integrated circuit. An ASIC is fabricated through applying masks to a silicon wafer in a fab. And so, everyone, I'm sure all of you heard about the chip shortage right now. The chip shortage is going on because these fabs, they require a lot of raw materials, mostly are nasty chemicals they use to make these chips, and of course with the supply chain being screwed up, they're not able to get those supplies, and thus they're not able to make chips. You need lots of different types of nasty acids called piranha acid, which is the nastiest kind of acid there is, and lots of hydrochloric acid and photoresist and lots of stuff, not to mention silicon ingots. Pure silicon ingots, not the silicon dioxide you find on the beach or near your windows, but pure silicon crystals, which are very difficult to manufacture because they have to be grown. So that's what the chip shortage is all about. But those are for ASICs. These are FPGAs that have been prefabricated, but they can mimic an ASIC essentially, but they run slower. So that's an FPGA. And so we're using these FPGA boards. So an FPGA by itself is useless, even if you can configure it, because it has to be connected to stuff. It has to be wired into peripherals. And so the reason we chose this board is because it's got a ton of peripherals, and it's almost indestructible. So as opposed to like the Atmel chips that we used 2 years ago in this class that are very destructible, these are indestructible, essentially. So the idea is they have the FPGA kind of in the middle, and then they got a gazillion components on the board. And that's also why these are so expensive, is because there's a lot of, as you might imagine, a lot of effort required to solder all these components on. But we've got 7-segment displays, LCD switches, buttons. There's like 4 or 5 different kinds of memories on this thing. There's all kinds of ports. There's several analog to digital converters. There's several different types of USB. There's video, there's sound, there's infrared, there's high-speed serial, there's SMA connectors for high-speed clocks, there's LEDs, SD card, tons and tons of stuff. Network, dual gigabit Ethernet networking. So it has a lot of stuff on it. And so basically, if you want to use any, it's designed to be a teaching board, basically. So the idea is that you could do a lot of stuff with this. People, build video games on these things, or robots. There's all kinds of stuff you can use. But basically, you choose which peripherals you want to use, and then you configure the FPGA to talk to those peripherals. So as you might imagine, whenever you use those, there's a lot of interfacing involved, and that's what this course is mainly about. Okay, so we're going to be using a tool called Quartus to configure this. Now this FPGA was made by a company called Altera, who were bought by Intel, so now they're Intel FPGAs technically. Although you may still see some references to Altera, but that's slowly changing to everything says Intel now generally. So Quartus is the CAD tool that we're using for this class. Is the same one used for 611 and 313 as well. And so Quartus basically is a tool that allows you to take Verilog code and convert it into a form where you can program the FPGA. That's essentially what it does. Now in this class, we're going to take that a step further, like we do in 313. Instead of having you use Verilog directly, and we will be learning Verilog in this class, but initially we're going to use something called Platform Designer, which is a separate tool, although it's still kind of under the umbrella of Quartus. And it allows you to construct a platform, whereas a platform means it's got a processor, a bus, and a bunch of peripherals in a system on chip. So basically that's the same kind of thing, the same kind of architecture you have on your phone's processor. But now, because you're building this on FPGA, you can customize it for the application that you want, right? Whereas the one on your phone is an ASIC and it's fixed, right? So that's Platform Designer. And then in previous years, we used Eclipse to write the software for the processor that we put on the FPGA, and now we're using command line tools because they're a little bit more reliable. One thing you should understand though is all these tools are really flaky. Even though they've been around for a long time and they're very expensive, they're all very flaky, and I never have been able to figure out why that is. The rationale I've always used is that they're designed by engineers that aren't good programmers, basically. So this isn't like using Microsoft PowerPoint. These are very flaky tools. They crash a lot and they're not documented. Okay. The other thing about these tools too, I'll mention real quick that you should be aware. They can be kind of slow, and the reason why they're slow is because when you actually run a compile job through these things, they use like a weird combination of natively compiled C, Java, and Perl that all work together. Instead of just relying on a single language, they use like an amalgamation of different languages that make these things work. And Tickle, which is another scripting language. As I mentioned, okay, I already talked about that. Oh, one thing I want to mention here too is that, so just to kind of explain this again and make it a bit more clear. So the FPGA allows you to put any arbitrary digital logic, into existence. Because we're using Platform Designer, we're actually creating what's known as a soft core processor, which is a processor. It's a MIPS processor called the Neos 2 that is designed in Verilog and put on the FPGA. And then you can write C code and compiled C code for that processor, right? And then if you want, you can also design custom hardware components as well. The code that you write on that processor is bare metal code, meaning that there's no operating system. Now you can run an operating system on that processor, but we're not going to do it because it takes even longer to get all that set up with the bootloader and everything. So it is, in theory, possible to get Linux running on this board. We're just going to be running it in bare metal. Bare metal code means that you write code that runs directly on the CPU without an operating system kind of running underneath of it. And so your code fundamentally runs in an infinite loop because if it returns, there's nothing to return to. It just crashes the system if you return from the main function. However, bare metal code is a little bit of a misnomer because in reality, you still have a very thin layer of software that you can use to help. It's not just your code and your code only. There's a layer of code called the hardware abstraction layer. And it's not an operating system per se, but it fills some of the duties of an operating system. It provides some drivers for you, basically, that we can use. Okay? All right, so that's the BSP. Now, the BSP is customized for the hardware, though. So every time you regenerate your hardware, you have to regenerate the BSP. The BSP is like a software layer that has to be generated specifically for your hardware setup. Does that make sense? Okay, I told you it's going to get a little complicated, but once you start working with it, it'll make sense. Okay, so to launch Quartus, you just type Quartus. So I'm going to go ahead and start doing that. So I have a, hopefully you guys can see that. So I've got, yes?
I'm sorry, what is the BSP? You said that you have to build it whenever you change your hardware, and then the BSP is basically the software. So what is it in specifics?
The BSP is a hardware abstraction layer, meaning that it'll convert, and remember at the beginning of this class we talked about how software and hardware communicate. It does it through interrupts and it does it through programmed I/O. Instead of having to use those things every single time you want to talk to a peripheral, which in some cases, if you're talking to something like a USB or an Ethernet, it would be massively complex for you to do that. So the hardware abstraction layer has some of the, like, basically drivers in there. So instead of having to directly interact with hardware with your code, you could do it through a little bit of like a function they provide, basically. So instead of having to tell the UART controller, all right, UART controller, set up for 57,600 baud and 1 stop bit, you just say printf, and it goes through it because the printf is implemented by the HAL, the hardware abstraction layer, right? So it simplifies things a bit. You don't have to use it. You can just write code, you can just put machine code on this thing if you want. But the hardware abstraction layer, it makes it a little bit like programming a real computer, but it's, there's no exception handling in it. So if you crash your program, it bricks the board. I mean, not permanently bricks it, but crashes the hardware and makes it useless until you reconfigure the FPGA or reload your software. There's no like segmentation fault or anything like that. There's no safety net like you have in Linux. If you read address 0, it just crashes. In here, if you read address 0, the board just stops working. Yes?
But it is still possible to do your own exception handling, right?
Sure, yeah. Yes, you can. Yeah, we haven't really, yeah, you can. We haven't done, the problem with the memory part that I was referring to is that you need a memory management unit to do that kind of memory checking, and the Neos processor actually does have that as an option. We don't usually use it. We just use a physical memory space. So with physical memory, it's hard to catch memory protection errors, right? You can if you turn on the MMU. We've never actually done it. You're welcome to try. But normally if you have the MMU turned on, you need an operating system for that. Any kind of bare metal programming. I've never seen a bare metal environment that uses an MMU. That doesn't mean it's not been done, but I've never seen it happen. Usually it's physical memory addresses when you're doing bare metal. Okay, so, and by the way, BSP stands for Board Support Package, which makes no sense to me at all, because it's really a hardware abstraction layer. I don't know where the board support package comes from, because it's not even supporting a board, it's supporting the hardware and the platform that you design. So that makes no sense. So I still call it the BSP, but the acronym doesn't make any sense to me. Okay, so you launch Quartus, which is Quartus. You're going to get this window. And again, some of you, this might be old news for any of you that have taken a course with these boards already. I'll try to get through this as quick as I can. I'm also going to try to follow the slides too, so when you do this, you can go back and refer to these as well. Okay, so, all right. So the first thing we want to do is create a new project. So we're going to say File, New, Project, hit OK, go Next. Okay, so the working directory is, I'm going to call it Lights. It's the name I usually use. So right now, this is on my virtual machine, and the virtual machine user is CSCE 611, so just ignore that. This would normally be your username, and then you would just add the name of your project at the end of that, and then you would give your project the same name as that directory. I'm going to just call it lights because ultimately, usually the first project blinks lights. It's a typical hello world for a board. So I hit next on there. Do you want to create it? Yes. We'll create it as an empty project, and okay, so here's the part that's a little obnoxious. So there's like a gazillion different FPGAs out there. There is a shocking amount. But the problem is whenever you have to set up the specific FPGA, not only the FPGA, but what package it's in and the speed grade. The package being, the ceramic thing, the thing you actually see when you look at the board with the pins on it, the thing that's on the circuit board, that's the package. You can have the same FPGA in multiple packages, which is pretty true for any chip. And then you have to also specify the speed grade. Each FPGA has a speed grade, meaning that some of them that come off the fab can run faster than others, and those are given a higher speed grade. So in this case, the type of FPGA we're using is called a Cyclone 4E. And the package is, this is basically just a filter because there's so many options at the bottom, but we're going to say FPGA, which stands for Flip Chip Ball Grid Array. The pin count is, I don't remember. Hold on. Let me refer to my slides. 780, speed grade 7. Yeah, sorry. 780, and the speed grade is, core speed grade is 7. And then even once you pick all those, you still have a few options here. The one we want is the 115 is actually the biggest size. So the EP4CE 115 F2 C7, F2 9C7. So the 115 stands for 115,000 gates, reconfigurable logic gates. That's the capacity of the chip. The 7 is the speed grade. The F is the flip chip. I don't know what the 29 is. Maybe that's part of the package name. And the EP4CE is the Cyclone 4E. So that's just the part number. I hit next on there, and then next, whatever, finish. Okay, so that creates a new project. Okay, then according to the slides here, the next step is, okay, so there's, this sets up the FPGA but doesn't set up the board. And that's important because the FPGA, once you set up the FPGA in the package, now Quartus knows how many pins there are. It's like, oh, there's 780 pins. About half of those pins are going to be non-reconfigurable pins, and the other half are reconfigurable in the sense that you can use them for whatever you want. However, you really can't because when they made this circuit board, they had to solder those pins to specific components, right? So whoever made this board decided how they were going to connect each of the user configurable FPGA pins to the little things that they soldered on the board, right? And that information is in a tickle file. Tickle being a little script, right, that sets up those pin mappings. So we are going to give you that file, but you have to load that in manually. So I'm going to open up Chrome. Come on, Chrome. So I linked the file on Blackboard, on Dropbox. Not Blackboard, Dropbox rather, sorry. And I just crashed my whole VM. Wow, awesome. Okay. Well, let me, wrong one. Let me start that back up again. In the meantime, I'm just gonna download it in, on here. So if you go to Blackboard and go to the course page, you will see a file at the top called DE2-115 Quartus Project Settings file. Now if you click on it, it's a text file, so it'll actually display the contents. Now this thing actually has, it actually has a section where it also sets the FPGA up here. Although for whatever reason, I don't know why this is exactly, but if you don't set up the FPGA part number when you set up the project and you just load this in expecting it to use the part number there, for whatever reason it doesn't work. I haven't figured that out yet, so it's a little redundant. But the important part is down here where you see there's a section for LEDs, SMA, LEDs, key, switches, those little toggle switches. And so every one of these things sets up an I/O pin, an input or an output or an in-out pin for each of the peripherals on the board. And this just sets them all up as an I/O standard 2.5 volt, because the FPGAs have reconfigurable I/O buffers. They can operate at different voltages and differential mode and single-ended mode. They're pretty flexible. But after you do that, you also have to actually associate them with an actual pin. And so you can see here it says set location assignment pin C25. C is the row, 25 is the column, and that pin is Ethernet 1 transmit data bit 0, right? So every one of the pins that goes out is associated not only with an I/O voltage level, but a pin as well. So that's the information we want to get out of this file. Okay, so I'm going to download that by just doing a right click and say save as, because it's otherwise it'll just show it in the web browser. So we'll say save as. And I'll just stick it on my desktop for now. And oh, it's already there. And then also there's another file there called lights.svg. That is the top level file that we're going to use for Quartus. So that's the top level file, meaning that it's going to basically create a wrapper between the pins on the FPGA and the system we're going to build in Platform Designer. So you want to download that one as well. So I'm going to grab a copy of that one and save it, and it's also there already. Okay. Alrighty, so let's get this started. I think it crashed because I got a little too aggressive with my VM settings. Okay, here we go. All right, so we come back into our terminal. And all right, so let's go to Quartus. And so if I go into the lights directory, by the way, that was the directory that I created when I created the project. You'll notice it's basically empty. There is a lights.qpf and qsf in there. Those are the two files that make up the project, both of which are Tickle script files. So inside of Quartus, I will just open that project. So you can go File, Open, Recent Projects, open that up, and it'll open that project. Now we go back to the slides here, see what the next step is. Okay, so we're going to add that lights.sv, or we're going to import those assignments I was talking about and add lights.sv. So let's do that as soon as it opens the project. You can see what I mean about these tools being kind of clunky. The project is empty, and so there's no excuse for it to take this long. But notice it's also updating this IP catalog over here, so that's probably why it's slow. Okay, so I got lights here. So I'm going to go to Assignments, Import Assignments, and then I'm going to, I have to copy that file first, sorry. I'm going to copy the file that I downloaded. So copy, what was it called? DE2, yeah, something or other. And then lights.svg. To here. All right, so we got both files. We go back to Quartus. You say import assignments. I'm going to find that DE2 115 pin assignments. I hit OK on that, and that'll import the assignments. It says 1,048 assignments were written out of 1,065 read. And then under assignment settings. Now this is a little weird, but you have to go into assignment settings to add files. It's a little non-intuitive, but I'm going to add that lights.sv here as well. So I'm going to add that, and then just I've added that, and I need to scale. All right. There we go. Okay, and then I'm gonna hit OK on there. Okay, so now if I go over here to hierarchy and I go to files, I've got the lights.sv, and you can see it there. I'm gonna right click and say set as top level entity. Okay, so let me quickly show you what's in here. It's pretty simple. The top level module name is called lights. The matches what the project name is. All of the, and I'm going to talk about what this means when I get into system Verilog. Some of you may know this if you've taken 611 already. But basically, all these inputs and outputs have to match the names that were given in that QSF file, right? So there's a finite number of possible IOs I can have on my top level module. Does that make sense? So these are the only way I can have the FPGA talk to the outside world is to have an input or output that matches one of the ones that's associated with a pin. If you put one here that's not associated with a pin, then it's not connected to anything because it won't know how to physically connect that to the outside world. You notice that basically I've got an input called clock 50, which is the 50 megahertz clock coming from a crystal. I got 4 keys, which are the buttons, and then I've got a whole bunch of things for DRAM. Because this is going to connect to a DRAM, the off-chip memory, and that DRAM, even though it's one DRAM channel, it's comprised of a whole bunch of individual signals that together create that channel, because it's a protocol much like SPI has 4 signals that make up one channel. DRAM has more than that, but it's basically a group of signals that make up a signal channel. You guys with me? Okay, all right, so now, inside the system I have nothing other than a Neo system, which I called U0. I didn't call it that, I copied this from the template it generates, but so the Neo system, and then the Neo system has pins that I just basically connected directly to here. So all this is a wrapper. It doesn't do anything. It just changes the name from this pins on the Neos to the pins on the FPGA. That's it, right? So that's why I don't want to make a big deal out of this, because it just changes names. Yeah, but the Neo system doesn't exist yet. We haven't made it yet, so we have to make it, so we're going to do that now. So we're going to go over here to Tools, and we're going to go to Platform Designer. Make sure I'm not missing a step here. Yes, I'm not missing a step. Okay, all right. So Platform Designer is a separate design tool that once it comes up, oh, there it is. There it is, it's coming up. Okay, so this is the Platform Designer GUI, and the idea is that we're going to put a bunch of components in here, and then they're going to get connected on this column. So it's like a table, and this is the name of the component, and then over here we're going to make connections between things. So these are going to be on-chip connections that uses something called the Avalon bus, which is an on-chip bus. High-speed bus that works on chip. It's not a serial bus like SPI and I2C or UART. It's a parallel bus that in this case, I think it's 32 bits of data. I think these are all 32-bit wide. You guys with me? Okay, so the first thing we want to do here is the only thing it gives us here initially is the clock. We want to add our processor. So we're going to, in the search box under the AIP catalog, you just search for Neos, and there's a thing called here, Neos embedded processor, Neos 2 processor. You double click that and it adds it to the system. Okay, so you add that and it's going to bring up this dialog box. Remember I told you that Neos has an MMU you can turn on? I mentioned that. If you did want to turn that on, it would be under MMU and MPU settings. So I can include an MMU, that's a virtual memory system that's used with an operating system. Obviously I'm not going to turn that on, I'll leave that off. In fact, I'm not going to mess with anything yet because you can change the cache size. So 4 kilobytes instruction cache right now, 2 kilobytes data cache. And you can make a bunch of changes here, but I don't want to do anything yet, so I'm just going to hit finish. And so I've got the Neos. So one thing you'll see here is it's starting to get a little complicated, but basically it's just clock and reset. Everything on here has a clock and a reset. Then you have a data master and an instruction master. Those are the 2 important ones for you, because the data master allows the processor to request to do reads for the instruction memory, and the data master allows it to do reads and writes for both the data memory and all the peripherals in the system. So the only thing you need to connect the instruction master to is the instruction memory, whatever that happens to be, but the data master probably should be connected to everything else, unless you have another master in there that you want to connect to something. But in this case, we're going to run everything from one processor. Does that make sense? Okay. All right. So then, and then there's some other things in there. There's a IRQ, which we talked about that, and then there's some debug inputs, and then there's a custom instruction master. That's pretty cool. That allows you to create your own instructions. So this is a MIPS processor. It has the standard MIPS instructions that you guys all learned in 212. But if you want to add your own instructions, you can add new instructions. And if you do, you would connect them to this instruction master port. Okay, so that's all we need for now. The next thing we want to add is we need to add an SDRAM interface. So that's the SDRAM controller that's going to talk to the RAM. This is the same kind of memory technology that you have in any computer. It's SDRAM. We're going to use the SDRAM controller for Intel FPGA IP. Now there are some settings we have to change in here. This is a 32-bit wide memory, chip select 1-bit, banks 4, row. There's 13 bits for row and 10 bits for column, I think. I gotta check, I don't remember. 13 row 10, yeah, 13 row 10 column. Okay. 13, 10, done. Hit OK, and then we got that. Okay, next is clock manager, another clock source, and our JTAG UART. Okay, and then we'll be done for now. So we need a clock manager. The clock manager. System and SDRAM clocks for DE series boards. So this is actually a component that's made specifically for this board. It came from the guy that runs the university program over at Altera and now Intel. Basically, it is it's a phase lock loop. It's an analog circuit that converts the 50 megahertz clock that comes in from the crystal to the clock speed and phase that's suitable for the SDRAM. You guys with me? Because the SDRAM doesn't run at the same speed as the processor, which I'm sure you guys know that. In a real computer, the SDRAM runs at like 800 megahertz and your CPU runs at 4 gigahertz. So there's a big difference in those two clock speeds. I'm going to go ahead and it's a DE2115. You just hit finish on that. Nothing to change there. And then you have to also add, and this is something that's a little obnoxious, but you have to add this clock source because so the problem is that the clock manager creates a 27 megahertz or whatever the speed is for the off-chip SDRAM, and you're going to use that to clock your SDRAM controller. The problem is that the SDRAM itself needs that same clock. You have to bring it off chip, and the only way to get the SDRAM clock off chip is to add this clock source, which basically just adds a port. So it doesn't really do anything other than provides a way to get the clock, the SDRAM clock off the chip. And then finally, we're going to add the UART, which is a way to get a console connection. Now we talked about how UART works in the class. This thing, JTAG UART for Intel FPGA. This thing is a UART that actually runs over the JTAG. The JTAG is it's like a side channel debug port to the FPGA. And because we have this really cool thing called a USB blaster that Altera uses, the USB blaster allows you to piggyback a UART connection over the programming cable. Right, so when you program the FPGA from your workstation, you can use the same cable to print Hello World over it, which is pretty cool. And you might think, well, don't they all have that? No. The other FPGA company, Xilinx, does not. You need 2 separate cables for that. And then this thing, and then this UART, integrates with everything. So I think that's all we need, right? Processor, SDRAM, clock manager, clock source, UART. Yep, we're done. Okay, now is the hard part, though. Now we got to connect everything. So we have all the stuff here, but they're not connected. So this is probably the trickiest part here, but you only have to do it once. You do it once. You can add to it after you do it once, but once you do it once, then you can write different software and run different software on here. Okay, so the first thing you want to do is, I'm just going to follow the slide so I don't make a mistake. Okay, so I'm going to start with the clock 0 component. I'm going to connect the clock output to the ref clock on the PLL. Okay, so the first thing that happens is we have 2 clock sources in here. One of them is used for input and one of them is used for output. This one's your input one. So the clock comes in and you can see, I don't know if you can see it in the back, but you see there's a little port here? There's a little pin and it says export clock. That means that this is a pin that's exposed and it's an input pin called clock, right? So this is how we're going to clock the whole system. The clock's going to come in here, but we have to run it to the phase lock loop because this is only a reference clock and the phase lock loop is what's going to provide our actual clock. Now you might say, why not just use that as your clock? You can, but then you can't change the speed. But we're not going to change the speed anyway. But it's also a messy clock. It's coming off of a piezoelectric crystal. It's not a good clock signal. It's dirty, it's noisy. It's coming from a crystal. We want to clean it up and so use this phase lock loop to make it into a cleaner signal. So we're going to take this clock output and we're going to trace this down and we're going to go down to this phase lock loop thing and we're going to connect it. You see there's a bubble right there? So this turns into like a, I don't know if you guys ever studied programmable logic arrays, PLAs, if you talked about that in 211. PLAs have like a vertical wires and horizontal wires, and then you can connect, you can make connections to connect any horizontal to any vertical wire. It's basically what this is. This is a virtual PLA. So the idea is that I'm going to trace this clock output down, and I'm going to make a connection to this reference clock input by clicking that little bubble there. You might be saying, like, there's got to be a better way to do that than finding bubbles in that thing. This is ridiculous. Nah, maybe with tickle commands, but I don't see a tickle console here, so unclear. Unclear how to do it. I don't know how else to do this, but it is kind of silly. But yeah, so we're going to make this connection here. All right, now once you make the connection, look, it highlights that wire, so now you can see it's clearly connected there, right? All right, so now we've got the reference clock. Now we've got this thing called sys clock, which is the output, and we're going to use this as the clock for our Neos processor. So bink, connect that. And we're going to use it for, not the SD-RAM controller, we have our own clock for that. We're going to use it for the UART. So bink, and is that it? I guess that's it for now. Yeah, okay. Now, there's also a reset input, which is going to be connected to one of the switches or the buttons on the board. That reset, you see there's a reset clock in reset, has an input export called reset. So that's the pin, and the corresponding output for that is called clock reset. And we're just going to use the raw reset. Directly from the switch, we're going to use that to reset all our stuff. You might say, well, wait, isn't that dangerous? I mean, that button needs to be debounced, right? Isn't it going to you're going to push it and it's going to be bouncing around and stuff? Yeah, seems to work though for us. I don't know if there's an integrated debouncer in these buttons or what, but it's always worked to do it that way. And that's how the templates work that come with the board. So I'm going to take this reset output here and I'm going to connect it to the reset on the CPU and the reset on the SD-RAM controller and the reset on the phase lock loop and the reset, I won't connect that one, and the reset on the JTAG UART. All right, so I got my resets wired up. Okay. Now, on the Neos processor, we have a data master and an instruction master. Right now, they're both looped back to this debug port. I don't know why they do that. Seems like that's something that can be done internally. But for whatever reason, the data master and the instruction master loop back to this debug because this way we can debug with it. We can monitor stuff over JTAG. So that's why they do it. I just don't know why they do it externally. But we also want to connect those to the SD-RAM. So we're going to take the instruction master and the data master, and we're going to connect them both to the slave port on the SD-RAM controller because both our instructions and data come from the SD-RAM. Yes?
Sorry, but why do you need 2 different clock units on this?
So that's a good question. This clock is used to input as an input for clock and reset. So this is used to create an input port for both the reference clock coming from the crystal externally and the reset button. The other clock, this one, is used for an output port to get the SD-RAM clock, which is generated internally, out of the FPGA to the physical SD-RAM memory on the chip.
So there
right.
are
Yes, yes. You can't use the same clock source for input and output. I don't know why.
Is that why you were saying that the competitors to our chip needed 2 wires, is because the input and the output are fundamentally different?
That's right, but that was referring to the programming cable and the console UART connection. But yeah, it's kind of like that. Yeah,
Okay.
yeah. Yeah, you know, what's funny is that the older versions of the software didn't require this, and there may be a way to work around this actually that I haven't found yet. But right now, this is the only way to do it, because if you don't add this, you get all those DRAM. Let me show you. Wait, actually, let's go back to Quartus, and I'll show you exactly what I'm talking about. So this is I don't know if you can read that from back there, but if you look at the DRAM ports, there's a 13-bit address, a 2-bit bank address, column access strobe, clock enable, chip select, data, 32 bits, obviously. DQM, which is the byte enable, so which byte of the 32 bits you want to enable. Usually it's all 4, but sometimes you just want to have individual bytes. Row access strobe, column access strobe, write enable, and then clock. There's an output called DRAM clock. But when you only add the DRAM controller to the system, it doesn't create the clock output, so we're doing that explicitly. I probably confused you even more, but that's that's basically the idea, is that we need to be able to drive this DRAM clock output because it's physically connected to a wire that goes to the DRAM chip. It's the only way to get a clock for that. Okay, so back to here. So we've got mastership of the SDRAM. Now for the JTAG UART, we need to master that too, but only the data master, not the instruction master. Because I'm not going to get instructions from the JTAG. I'm only going to use the data to drive that because it's a peripheral for just outputting stuff. Did I get that right? Please tell me I got that right. Data master, yeah. All right. And then if you look at the PLL here, this is the PLL, the SDRAM. The Qsys SDRAM PLL. It's really the clock source. It puts out a Qsys clock, which we've already connected. There's also an SDRAM clock. We have to connect that to 2 things. The first is the DRAM controller, which is here, and this clock output that the clock in on this clock source that I was just telling you about. So if I click that, you can see it fans out to 2 things. SDRAM clock gets generated, it goes to the SDRAM controller, and it goes to this output pin. Okay? I told you it was going to be a little confusing, but like I said, this is literally what, this is the kind of process they use, like when Apple creates a new chip for the iPhone. They pick components from a repertoire of IP blocks, and then they connect them on a common on-chip bus, basically doing this. Not all components connect all the other components, but so you have to be careful how the connections are made. All right, and then I think that's about it. There's a few other minor things we have to do. This clock source, we have to export this clock output. So I'm going to double click that to export, and I'm going to call it SDRAM clock. SDRAM underscore CLK, and I have to export the SDRAM controller wire, which I'll just give it the default name. And I think that's about it, I think. Oh, in this IRQ. The UART has an IRQ. So that way, if you're communicating with a user at a terminal and you want to wait till the user hits a key, like the CPU has to be alerted to that. If you're, like you say, press any key, right? How's the CPU know you've pressed a key? There needs to be an interrupt. Luckily, there's only one thing on this whole design that can accept an interrupt, and that's the CPU. So that's a no-brainer. You just hit the one. There's just one option there. So we'll just connect that wire there. It's the only possibility. I think that's it. Let's go back, double check the slide. Did I forget anything? Nope. I think we're good. Okay, one other thing I want to point out is you'll notice that there's a column here called base and end. This is the programmed I/O thing that I covered, right? This is kind of like the quiz question I asked you about. You have a peripheral and has a starting address and an ending address. So every peripheral in here is going to have an address range and also an IRQ, potentially. the addresses need to be specified. Sometimes they're added automatically, but sometimes you have to explicitly tell the thing to generate addresses automatically. So you go up to System and you say assign base addresses for that. Okay? Notice I cleared up a lot of these errors down here by doing that. You guys with me? Now, by the way, for example, if I were running Linux on here, Linux would have to know these before it even boots the kernel, which is why, in order to boot Linux, you need a kernel and a device tree file. You need two things to boot a Linux machine. This is the information in the device tree, these address ranges for the peripherals. Okay? So, you know, I would have to create a custom device tree if I wanted to boot Linux on here, in other words, right? Because I have the ability to change those addresses, and if I change the address in hardware, it needs to be updated in the operating system, or in this case, in the HAL. Okay, so the last errors I have down here are because the compiler is not going to know, when I compile code, it's got to know where to link the code, what memory to link it into. And so for that, I have to go up to the Neo settings here again, and I can only do this now that I've added the memory. And I have to go to this Vectors tab, and I have to say that I have to specify the SDRAM controller as the place where my data, my instructions are, my data and my instructions. So in the way that you do it is not by saying this is where your data and your instructions are. You do it by saying this is where my reset vector is, which is a really indirect, weird way of doing it. I don't know why they haven't changed that, but that's the way you specify your target memory. And now I've got no error, so I'm good to go. So now I'm just going to say, any questions about that, by the way? Okay, so I've now created a whole system. I've got a CPU, I've got a console, I've got an SDRAM controller, and I've got, well, that's it so far. Eventually we're going to add some other ports, you know, GPIO, we're going to add some ability to do some other stuff. But for now, we got enough here to run. Oh, by the way, there's 128 megabytes of SDRAM on here. You might say, why do you even use an SDRAM? Why not just use on-chip memory for your program? You could, but the FPGA only has about like 64 kilobytes, and I don't think that's enough to store the HAL, the BSP. The BSP is huge. It's it's bigger than it ought to be. So I don't know about fitting that all on chip. So we're going to use the off-chip memory for that. Okay, I think we're ready to go. I'm just going to hit Generate HDL, Generate. Oh, one more thing. Sorry, cancel. So one thing I did forget. We want to say File, Save As, and I want to give a name Neos_system for this. That's important because that's how I refer to it in the top level design. And now I'm going to hit. So it saves it. It takes an inordinate amount of time to save as usual because everything these CAD tools do takes 10 times longer than it ought to. There, it finally saved it, so now I can hit Generate HDL and hit Generate, and now it's going to run a bunch of Java/Perl hybrid monstrosity Frankenstein stuff to generate this. But what it's doing now is it's going to generate the system Verilog code needed to essentially assemble this whole thing in hardware, right? So you could design this by hand, but it would take forever. Basically, what this is doing is automating the process of designing a very complex system. Right. Now, if you want to add stuff to this that you design by hand, you're able to do that. Like I can build my own IP module and I can add it. I can add my own little radar processing peripheral and just stick it into this system and then interact with it from my software if I want to. Or my own GPU. I can just drop my own GPU in there if I want. There's no GPUs for this thing, but I can make one if I wanted to. And if I did, I could put it in here. Okay, so that thing generated successfully. So that wasn't too bad. And now we go back to Quartus, and I'm going to just import that file. Now, it actually created a bunch of files, but the only one that you have to import is the Qsys file, the little file that contains all that information. So I'm going to go again to Assignments, Settings, Files, hit ... add neosystem.qsys, and hit OK, and it's in there. And then one last thing I need to do is, the only thing missing is that I've got all the pin mappings done, I got the design done, but the tools don't know what the clock speed is. It knows what the clock pin is, it knows what the clock name is, right? but it doesn't actually know what the clock speed is, which is important because when it converts this to hardware, to a programming file, it has to generate in a way that it can make timing, meaning that the logic is fast enough to keep up with the clock, that all the critical path inside the clock, the logic can be done in the clock period. You guys with me? So if you took 611, you know what I'm talking about. We cover that in 611, how that timing closure works. So how do I do that? I have to create a new file, which I'm actually going to do manually. This is going to be a synopsis design constraints file. And I'm going to say create underscore clock. And I don't remember exactly what the syntax is, so I have to refer to this. Dash name clock underscore 50. And then dash period 20. I'm just going to copy this actually. Copy and paste. If it lets me do that in the VM. It does. Okay, cool. So, so this says that my clock is clock 50. I'm going to get it from the clock 50 port. The period is 20 nanoseconds, which is 50 megahertz. And I'm going to derive PLL clocks, meaning that if this thing is a reference clock for a PLL, and that PLL is designed to multiply the clock frequency by a factor of 2, then just assume that the output of that has got to be at 100 megahertz. Right? So this is a derived PLL clocks. And that's it. We're now save it as SDC1, and we're good to go. Hit the go button. And now we'll compile this into hardware. So our objective here is to get something called an SOF file, a serial object file? Serial object file? SOF file. That's the file that actually you send to the FPGA to make the logic magically appear on it. That's the configuration file. Sometimes they call it the bitstream file. The reason they call it a bitstream file is that it goes into the FPGA through JTAG, and even though I haven't covered it yet, it is actually a topic in this lecture, but I'll come back to JTAG here in a minute. JTAG is like SPI and UART and I2C in that it is a bit serial protocol. So all the bits that configure the FPGA go in one by one, and that's why they call this a bitstream file. That's also why it takes a really long time to configure the FPGA, as you will see once I get the soft file to show you. Okay, now you'll notice that the tools are slow. This slowness is understandable though, because it's actually building the actual gates. It's taking it has to parse the system Verilog, it has to convert it to a netlist, which is a graph of logic gates, and then it has to map each of those logic gates onto the physical gates on the FPGA and then form connections between them. It takes a long time. It's an NP-complete problem to do optimally, but they use simulated annealing to do it quick. I mean, relatively quick, but it still takes a while as you're waiting for it here. And you're going to see a lot of messages. You're not going to understand any of these. Well, some of them you might, but mostly these right now it's just saying that it's finding all these modules that were generated by SOPC Builder, Platform Designer. So Platform Designer was a tool that we built the platform in. When we hit generate, it didn't generate just one file, it generated a couple dozen files, and now it's talking about all of those individual files here. Now we got some warnings. It's saying inside the SDRAM controller that I didn't even make, conditional expression evaluates to a constant. So shame on Intel. It wasn't my design. Quartus is complaining about it. Hundreds and hundreds and hundreds of messages will print as it compiles. This is another downside of these tools, because if there are any legitimate messages in here, things that you did wrong, you're probably going to miss them. So that's unfortunately, I never found a good solution to that. Yeah, PLL for D series boards is connected to a signal with 3, the formal blah blah blah. Yeah, not my problem. Hopefully it still works. Okay, so it's still generating, still compiling. While that's doing that, I want to just double check and make sure. Hopefully I didn't forget anything. I'm gonna have to, because if you do, you have to go back and recompile. So all of the steps are here. So I talked about that. Okay. So this is the next step, slide 18. We'll just wait till it finishes. It's almost done. Now this is taking a little longer than it would in the lab because I'm running a virtual machine on top of Windows. In the lab you're running Linux natively, so it's going to be faster. Also, those are desktop computers and this is a laptop, so it won't take quite this long. But compiling designs for an FPGA in general does take long. Yes?
Will we be doing this in the lab on Wednesday?
Yes. Yeah. So on Wednesday, my plan for today is I'm going to show you how to get this basic system set up, and then on Wednesday I'm going to give you another tutorial on how to actually add the components needed to talk to the lights on the board, to actually make it light up and do blinking lights. I don't have time to do that today, but I'm going to give you enough to print hello world, but not enough to blink lights. We'll do that on Wednesday. All right, still compiling, 98% on analysis. There we go, synthesis finished. These are all the steps it goes through: analysis and synthesis, fitter and assembler, and timing analysis. And we're done with, I think analysis and synthesis are usually the longest ones.
Yeah, the VM tax is really killing us here. In the labs, this runs dramatically faster.
Okay, now while that's running, I'm going to show you how to actually configure the FPGA. So we're going to do that in the command line too. There is a GUI for that, but I'm just going to show you how to do it in the command line. So first of all, in order to talk to the FPGA, you have to run a JTAG daemon. The way that works is JTAG is a protocol, and the way they handle that is they run a server that basically creates a JTAG connection to the FPGA. And then all the applications that want to use it just connect to that server over sockets, kind of like an internet program, right? Make sense? If any of you have ever done any Android development, you've also done this. The Android also uses JTAG when you plug in your Android phone and USB and connect it to the Android SDK. It uses the same kind of connection. When you launch ADB, Android Debugger, it's the same. It's basically the same as that. Okay, that's what this is. So we're going to run JTAG-D. Now the problem is, normally you would just run JTAG-D. However, there is a problem with the lab setup that I haven't been able to figure out. If you just run JTAG-D by itself, for whatever reason, it doesn't. You get an error. So we had to add this parameter to make it work. We didn't have to do this in years past. It's something that came up with the newer version of Quartus and the newer lab environment. Sorry, I screwed that up. So it's JTAG-D dash config, and then you just give it a long path to this parts list. Gives it the parts for the FPGA, and then -- user start, meaning that you're starting it manually. Now on my machine, I don't have user local third party, so I have to adjust the location of this. So I'll get that ready now. I have it in opt Intel FPGA 18.1 Quartus. Yeah. So I just have to modify the path that this file is in. So I'm going to run that. Why did I not get this earlier today? libccl ver cannot open share line. Okay. Okay, let's do it this way then. JTAG-D. Let's put that in again. But this time I'm going to specify a library path for it. You should not have to do this part in the lab. If you do, then I'll fix it. Opt Intel FPGA /18.1 /Quartus /Linux 64. Same thing. Okay. Well. Okay, that's not a big deal. I'm almost out of time here anyway. So. Okay, so actually, I'll tell you what. I will continue this in the lab. I don't know. This must be my VM setup, but I'm getting a libccl ver. Normally, you fix that by. Oh, I know why. I misspelled opt. That's why. Duh. There we go. Now it works. Sorry, I just misspelled. I had, instead of opt, I had top. Okay, that starts the JTAG, and then are we done compiling yet? Nope, still going. Okay, so it takes a while to almost done. 88 netlist writer. Look, at 99, almost done. That should just finish. Boom, done. Okay, good. Now to configure it, I just type neos2 configure sof, and the generated file is in a directory called output files. Now notice, by the way, I'm in the lights directory. I'm in my projects directory when I'm doing this. So relative to that, there's a subdirectory called output files, and the output file is called lights.sof. Okay, and this will configure it. Now, when I configure it, you're going to know it works because this thing is already configured, right? And it's blinking and stuff. As soon as I configure this guy, it's going to stop dead and go into my configuration. It's not, my configuration doesn't do any kind of blinking lights thing. So I'm going to hit enter on that, and there we go. Oh, you see it just stopped. Now, the thing about this is you'll notice that these lights, it's kind of interesting. These LEDs are dim, but they're on. Why are they dim? They're dim because I didn't connect them to anything. They're actually floating. The FPGA is not driving them at all with any voltage. And so the actual voltage is floating, and because these are active low LEDs, one side is tied to VDD and the other side is supposed to be tied to ground when you want to turn them on. When they're floating, you get a partial voltage drop over them, so they're kind of dim, right? That's what happens when they're not connected. So if your goal is to actually light these up and you see them dim like that, your connections are dead. There's something wrong, they're not connected. But I didn't actually connect them to anything in the FPGA design, which is why they're dead. It's also why the hex display went off. Now the LCD still says welcome to the Altera DE2-115, but that's because the LCD display has its own independent controller that remembers the last thing it was sent to print. And so that message will stay on there even though I don't have pins for the LCD either, right? Likewise, I don't have pins going to Ethernet. So if I plug this into Ethernet, the switch will be like, what? What is this? What? You know, the Ethernet switch will not see anything either, because again, I'm not driving. Well, they have an independent controller too, though, so they probably just have 0. Okay. Alrighty. So that's all I'm gonna have time. I'm gonna go through. I'll continue this in the lab, and we'll see. I'll show you how to set up the software and print Hello World and get the lights working. In the meantime, let's go over here to. I've got 5 minutes, right? 3:35. Yeah. So I've got 5 minutes. I want to just. Before you guys forget about the topics we were covering, I just want to revisit those. Now I have a quiz. Quiz 3 is posted. It's due in a week, but the quiz is going to cover some things I didn't get to today. So I will put that quiz off. I'll change the due date and let you know because it covers I2C material I haven't gotten to. But just to refresh your memory where we were, and we'll come back to this next lecture. Last week we talked about the push-pull interface. Which pulls a voltage up or down. You can't double drive that because if you pull one up and the other pulls down, you short circuit the thing. You can add tri-states to disconnect chips from the push-pull, or you can use an open drain, which is what SPI uses. I2C uses rather. SPI uses the other type. Open drain is where basically the bus, the wire, the shared wire, can have multiple peripherals on that wire, and there's a pull-up resistor. So if no one's actively pulling down, it's logic high. You guys with me? Unlike these LEDs, LEDs are not, these are not open drain. These LEDs are connected to push-pull drivers, and because I'm not push-pulling them, they're dead, or they're like dead. They're not, there's no pull-up resistor there. Well, actually in that case it would have to be opposite because they already have a pull-up on one side. But the point is that if no one's doing anything, it looks like a 1, right? Now if one of these guys pulls down, it becomes a 0, and although we do get more leakage current in that situation than you would with a push-pull, it's generally okay because it's still microamps of current. And the other advantage is that we can have multiple guys pull that down and it's not going to cause any problems. So we can have a conflict where two entities try to take mastership of the bus and they both pull it down, and it's no problem. Hopefully they can detect that happen, but it's not going to blow the chip up. You guys with me? Okay, so where am I going with this? Well, I squared C kind of depends on this concept. So I squared C has two wires, SDA and SCL. SDA is the data, SCL is the clock. And whoever is the master of the bus at the time, and anyone can be master, you just have to claim mastership, whoever's master is going to be driving the clock. So it's still a synchronous interface, you still have a clock signal in there, but anyone's allowed to drive it now. And whoever's driving it determines the clock speed of the thing. And whoever drives the I squared C is going to determine how fast data is going to move through that. Don't overdo it, because the slaves may not be able to keep up with you. Okay, and then the data, on the other hand, now this is an interesting thing. If I just want to get one thing out there for you guys to keep in mind for the next lecture. The master drives the clock, but the data is driven by the master and the slave, even within the same transaction. So what happens is the master puts an address out like a header, and then it yields control of that same wire to the slave, who then responds with an acknowledgement. And then, if it's a read operation, the slave will then keep control of that wire and send the data back. And if it's a write operation, it'll yield control to the master, who will then continue driving the data. So what I'm saying is that even though the clock is driven by the master, like in SPI, the data line actually changes hands even within a transaction. It gets handed off. I send something, you send something. So it's only half duplex, unlike SPI. Remember, SPI was full duplex, wires going in either direction. Here there's one wire, only one entity can talk at a time, but that's okay, because remember in SPI, we had two wires, but we only used one of them at a time, right? What a waste, right? Whenever you did a transaction, one of the wires was just dead anyway. You had two wires, but it was enormously wasteful, whereas now there's one wire, and it's a little bit more complicated because we got to hand off control sometimes multiple times throughout a transaction, but it's only two wires. So it's only half the cost of SPI, and it's multi-master. So it's a lot nicer than SPI. Right? Make sense? Okay, so that's really the only thing I wanted to convey, because I will expand on that in the next lecture. And then I'll see you in lab, and we'll continue the demo. Thank you.